element, one-dimensional bar element, either in vertical direction or in horizontal direction, orthogonal direction. So it lies only in the general global coordinate system only. It is not a localized system. Local coordinate system, global coordinate system, they are coinciding one another. Suppose if I will consider a bar of length L and cross-sectional area A and modulus of elasticity of the material of the bar as E. Suppose if it is subjected to a load P causing a displacement delta. This is a small basic problem which you have already solved in strength of materials. A bar subjected to an axial load resulting in an axial deformation, and this deformation you can derive it as PL by AE. Correct? PL by AE. This you have already derived. I need not go much into the detail. Here now I will define only what is stiffness and flexibility associated with the bar element, either lying vertically or horizontally. There is no question of any transformation and all those things. We can treat this itself as the global axis. Load applied is in global direction, resulting in global direction displacement, which is given by this. So now first we take up, we relate this P in terms of this P is equal to AE by L into delta. So this I can write it as L by AE into P. So this relationship is relating displacement with the load. Displacement with the load means this we call it as the flexibility. Here force related to displacement, so this we call it as the stiffness. So already I defined how this, what is stiffness, what is flexibility, because it is only one load, there is only one coordinate system. With respect to one coordinate system, so your stiffness matrix or flexibility matrix, it has to be a 1 by 1 matrix only. This load is also 1 by 1, displacement is also 1 by 1 matrix. So this is with respect to bar element. This stiffness or flexibility matrix associated with bar type of element or truss element. If truss is not inclined member, if it is horizontal or vertical member, then you can use same thing. So the stiffness of at any end, one end only I am talking about, not both the ends. If you take both the ends, then it represents the stiffness matrix of that member, which is called member stiffness matrix. It is here I am defining only with respect to one joint or one node. So stiffness with respect to one node, it is AE by L for a bar element or one-dimensional axially loaded element. Or flexibility, in other words, we can define it as L by AE. With L, A, E, there are properties associated with the material that we will know well before the analysis of the structure. So this is another thing with respect to bar element or element subjected to only axial load. Here you can see flexibility and stiffness. They are inverse of another. Because it is L by AE, this is AE by L. Relationship existing between flexibility and stiffness for same coordinate, that you have to remember. That is for same direction. That is no direction or displacement for same direction. With flexibility and stiffness for same degree of freedom, they are one inverse of the other. F is equal to K inverse or K is equal to F inverse. That is another concept which you have to remember. If I ask you to prove, you can prove that flexibility is inverse of stiffness either with respect to a bar problem or with respect to a beam problem, which undergo only pure rotation only, not shear, or shear and moment also you can take it together. Next we will take another beam problem. You consider a beam problem. So I have considered here a bar problem and define what is flexibility and what is stiffness. So it is only single quantity. Now we take a beam problem and we derive the stiffness and flexibility coefficients for that. So you consider a beam element like this, which is subjected to the end moments. Always the moments we take it in the clockwise direction as the positive with respect to the coordinate system. So this is one coordinate, this is another coordinate. I have considered two coordinates. Here I have considered only one coordinate. Now here I have considered two coordinates. Two ends I have considered, that means it is a member. Here I didn't consider member, I consider only one point. Here also I can consider 2 points to 2 ends, it becomes a truss. Here I told A by L. So 2 points, one is opposite to the other because here whatever is happening, here equal and opposite will happen opposite to that. So the stiffness matrix of truss element is A by L, 1 into 1 minus 1 minus 1, 1. Automatically if you apply load here, so because of that there will be equal and opposite in the other direction. Then if you apply same load here, equal and opposite, so it's a 2 by 2 matrix that you can always generate it. So now with reference to beam problem, you consider a beam element with respect to subjected to moment. So this particular example what I am considering is from a practical beam example. Suppose if you take a continuous beam in practice having infinite length, I will consider only this intermediate beam to define what is stiffness and flexibility. I will consider this intermediate beam. This intermediate beam will be like this. So which has supports. Always here I cannot take both roller, it will be unstable. I will represent it hinge. The boundary conditions will not alter because this is also allow rotation, but translation of course beam we assume to be axially rigid, it doesn't matter. So I am without affecting the end boundary condition, I took up a beam. And because of this continuity, whatever may be loading, so this is a continuous joint which we can assume it to be fixed joint for all practical purpose. So originally it treated as a beam problem without any displacement, because that will be in equilibrium without any displacement. It's a beam problem, fixed problem. Whatever loading is there, due to that load, I have to find out fixed end moment. That's what you have done in slope deflection method. First you get the fixed end moment. So that fixed end moment I have applied here. That fixed end moments will always be acting at these two ends. So that is, I have considered a typical beam element from a continuous beam problem. So a beam subjected to end moments M1 and M2 having length L, flexural rigidity E. It is basically a bending member. Now this problem I can always consider for development of stiffness or flexibility. First I will take up to develop stiffness. Then we can take flexibility to develop stiffness. To develop stiffness matrix. So you consider a beam element of length L, flexural rigidity EI, subjected to N moments M1 and M2 as shown here with respect to global coordinate system. Now this, to derive this stiffness matrix or to develop the stiffness matrix, already I have defined stiffness matrix is the force due to unit displacement. So here I will remove both M1 and M2 to start with and apply only unit moments in the direction of M1 and M2 independently, separately. Then I will add, right? You will get this result. So then you consider this problem as combination of two problems. One is this applied moment m1 equals 1. I will apply to this end, then it will deflect. Of course, I will write it as a line element instead of that full rectangle type of thing. Line element, I will apply a unit moment there, then it will displace like that. Here, it will displace like this. So this I should not allow it to rotate. Other than I will apply unit moment only in one direction. Of course, when one unit is applied due to m1, I will simply multiply by whatever result I got, so that I will get what is due to this. So here, when I apply unit moment here I should not. This will result in say displacement d1 and this result in displacement d2. Here not unit moment, because stiffness matrix I am generating means I have to apply unit displacement. I define the stiffness as force developed due to unit displacement. I will apply a unit displacement here. I don't apply any displacement at the other end. Then due to unit displacement applied, the force developed here, that is your m1 force. It has been derived in slope deflection method. It is equal to 4EI by L. Here it is fixed. I am not allowing any displacement. So since it is fixed, here there has to be a moment developed, and that has to be 2EI by L, that is in the direction of m2. So next I will apply independently a unit displacement due to that d2. d2 is equal to 1. I will apply. When I apply unit moment, then without, of course, in the clockwise direction, here I don't apply any displacement. That means I fix it notionally. So here, due to this unit displacement, the force developed here is nothing but 4EI by L. Here it will be 2EI by L. So this you have already derived. Now since I am developing the stiffness matrix with respect to the two coordinates 1 and 2, so the size of stiffness matrix will be 2 by 2. Since it is with respect to two coordinates, it will be 2 by 2 matrix. Because here it is only with respect to one coordinate, it is only 1 by 1. Here it is with respect to two coordinates, it has to be 2 by 2. That you can say first. So to develop the stiffness matrix, since we are developing the stiffness matrix corresponding to the moment developed at the ends, so the size of the stiffness matrix has to be 2 by 2, and it is given by K11, K12, K21, K22. How do you define these elements or coefficients of this stiffness? Already I have defined the coefficient of stiffness matrix. K11 means K11 is the force developed at 1 due to unit displacement at 1 itself. In this case, I have applied a unit displacement of 1 here, whatever force developed, that is that K11. So that means this has to be K11. Force developed due to along 1 due to unit displacement at 1. So this K21 is the force developed at 2 due to unit displacement at 1. So this is nothing but your K21. So that means I am generating the stiffness matrix always column wise. In that stiffness matrix, first column I will get by applying unit displacement for the first coordinate. Second column you will generate by applying unit displacement with respect to second coordinate. These are the things which you have to remember while working the problem. I am giving the procedure. While working the problem, you have to follow the same thing. Then when I work the problem, I don't repeat all these things. Simply I will go on developing these values I have already given. You have to remember. Similarly, here I applied unit displacement here with respect to second coordinate. So this is the force. So that means this force is force developed at 2 due to unit displacement at 2 itself. So therefore this is nothing but K22. So here this is value is 1, 2. That means this is the force developed at 1 due to unit displacement at 2. So this has to be K12. So therefore now I have generated stiffness matrix of this beam element corresponding to known moments M1, M2 are corresponding to unknown displacement T1, T2 and relating T1 to M1, T2 to M2. Through that is these forces I am relating with this displacement by this stiffness matrix. Two quantities I have taken. Here I have taken only one force displacement. Here also two forces I am relating to two displacement by K. How to develop that K? I have explained here the procedure. So always to develop stiffness matrix, you have to give unit displacement. In that first you have to select the coordinate. In one direction you have to give unit displacement, restraining the other direction. That's very, very important. You have to restrain the other direction. Don't allow the other direction to move. Whatever forces develop in the two directions that you have to take. That will define the first column of the stiffness matrix. Similarly, give unit displacement in the second coordinate direction, find out the forces that defines that second column. So here the stiffness matrix of this element is 4EL by L, 2EL by L, 2EL by L, 4EL by L. Or it is simply 2EL by L into 2, 1, 1, 2. This is the stiffness matrix of the beam element relating the moment developed at the two ends. That's a fixed beam you assume like that. So you can now write the force M1, M2 is the K into D1, D2. Here M1, M2 on account of the load, equivalent joint load, you can determine on account of whatever load is coming, fixed end moment you can take, fixed end moment you can take that as the load, stiffness matrix you have generated, you can find displacement. This is exactly what I was telling. First, in the global, with respect to global coordinate system, given the load at joints, various joints, you find out the displacement first. Then go to the local coordinate system for finding out the member end forces. That is by slope deflection equation as said. So using this, you determine the displacement first, then take force displacement relationship, that slope deflection equation, arrive at the forces, left hand, MAB, MBA, and once this is known, whatever load is there, find out these shears also. That is the basic principle of matrix stiffness method of analysis. So likewise, if you come for flexibility, so you have to apply unit force. So now I have applied unit moment and got it. So to develop flexibility matrix, F. So for developing the flexibility matrix, I have to apply same beam with same coordinate system, because with this example itself, I will show that K is equal to F inverse or F is equal to K inverse. So I want to prove with the same example that already I have covered one example. So I will take here, so these are the moments M1, M2, due to this resulting displacement. So resulting displacement will be, because I have taken both clockwise direction, I will take like this. There also we should have taken like that itself. So this is D1, D2, M1, M2 to start with. D1, D2 will not be like that, it will be opposite to the other. So that you can just make that small correction here. The net displacement will be like that. That's all. Because both I am taking clockwise. In that clockwise direction only, rotation also should be there in the direction of force. So if I take this here also, first I will take individually, I will apply this one by one as I did that independently and add them together, I will get the flexibility relationship. So you take this beam, simple beam as it is, individually, you apply a unit force now. Here I apply unit displacement, now I will apply unit force. So because of this unit force I applied, it will deform like that. So I will find out what all the displacement produced. Then apply unit displacement forces level. Here apply unit force, find the displacement. So the displacement due to unit force, that also we can prove it. It will be at the near end, it will be L by 3I. Here it will be L by 6I. Here it is in the clockwise direction, here it is in the anti-clockwise direction. So that is minus L by 6I. Similarly, I will apply unit force in the direction of the coordinate 2. Here M2 equals 1, you can apply. So it will reflect in this pattern. So this is the displacement here, this is the displacement developed here, and this will be L by 3I. Here this will be minus L by 6I. So therefore, now you can relate this displacement with the force. D1, D2, you can relate with the force through flexibility matrix. This flexibility matrix, this is M1, M2. This is nothing but your F11 using same type of notation. This is F11. Yes. So it is displacement along 1. This is the coordinate 1, coordinate 2, along 1 due to unit force at 1. This is F21. This is F12. This is F22. So if I put that value here, F11 is L by 3I and all, I will take out L by 6CI outside and get here 2. F11 is L by 3I. If I write that 2 into L by 6I, it is L by 3I. Then this will be minus 1, and this is 2. So this is nothing but your flexibility matrix for the same coordinate, for the same thing. Now if you see here K and F, so if you find the inverse of this K matrix, so K inverse is nothing but this is L by 2EI into 1 over determinant of this, that is 4 minus 1, that is nothing but 3 into adjoint of cofactors. This adjoint is 2. Here next I will write, take this, I will write there on the row. So automatically it is transpose of adjoint. So it is minus 1 because it is minus of that determinant. So here it is minus 1, 2. So this is nothing but L by 6CI 2 minus 1, minus 1, 2. So this F is equal to K and F is equal to K inverse or vice versa. If you take this inverse, you will get that. So this is also proved. Basic concept of stiffness, flexibility, and the methodology involved in our matrix stiffness method of analysis that also have explained. That is, you have to generate stiffness matrix by this procedure. All these fundamental basic concepts you have already developed because of unit translation. That is 12A by L cube, 6A by L square, those things also known. Remembering those fundamental things, you can work any problem. So from next onwards, we will take up examples straight away. You remember all these concepts. So next we will take up beam And frame problem, first we will work. Problem is with the truss. Truss is element approach, not this system approach. That I will take up at the end. Element approach also we have to do it. I will take up that next. Right now, beam and frame problem. First by stiffness method only I will take up. Next, flexibility method, both we will finish it.